A vector field f in R2 or in R3 is a gradient field if there exists a scalar function f such that the gradient of f equals the vector field. As we have learned earlier, a vector field f is a conservative vector field or a gradient field if there exists a scalar function f such that the gradient of f equals f. So we can say it's conservative if it's a gradient field, which means there's an f such that the gradient of f equals f. And it says in this situation, f is called a potential function of f, vector field f. Conservative vector fields arise in many applications, particularly in physics. The reason such fields are called conservative is that they model forces of physical systems in which energy is conserved. We study conservative vector fields in more detail later in this chapter. So, if it's a conservative vector field, it has a potential function, which means it's a gradient field, which means there's an f such that if I take the gradient, that's going to equal the vector field. All right, so there's a lot of vocab here. So we got gradient field, potential function, and conservative vector fields. So those are the three big ideas here. So take a look at the problem below. It says, for the following exercises, find the gradient vector field of each function f. So looking at number 15 here, essentially all we have to do is find the gradient. So the gradient of f is equal to, now keep in mind that means fx comma fy. That's how the gradient works, if you forgot. Those are just partials with respect to x, partial with respect to y. So then this vector is going to be sine of y, comma, negative sine of y. So now this would be the new vector, gradient vector field, or a new gradient field, or vector field. So that's the first one. That's all we have to do here. And it says, for the following exercises, find the gradient vector field for each function f. So that's all we're doing is just partial derivatives here. And so for 16 then, that's going to be f of x, and I'm just going to write it out. yz equaling ze to the negative xy. So then my f, and this is my gradient vector field, is going to equal, first with respect to x, so negative yz e to the negative xy. And then for the y value, or y component, negative xz e to the negative xy. Now again, remember this is a chain rule here. Derivative of e to the x is e to the x, and then the chain of the inside. So that's really what I'm doing here for these partial derivatives. And the last one's going to be an fz. So for this one, just to give you a heads up here, this is going to be fx, fy, fz. And that's what we end up with on the end there. So this has three components because it's f, x, y, z. Okay, so then for the last one, then z is just going to be e to the negative xy. So there's our new gradient vector field, which this would be conservative because it contains, because it's a gradient vector field, and because it's a gradient vector field, it has a scalar function f. So we would say it's a potential, the potential function is the f. It is a conservative vector field because it has a potential function, or also because it's a gradient field. So for those two reasons, we can say it's conservative. So there's our answers. We're going to get more into that later on, like it says in the text there. Later on in the chapter, we're going to see more of this. So later on, we'll be given a vector, a vector field, and from that vector field, we can find the potential function if it exists. And again, it's going to exist if the vector field is a conservative vector field. But for our two answers, it would be this one here, and for the other one, it would be this one here. All right, so there we go.